All right, today we're going to unlock a pretty fundamental secret of engineering. But here's the cool part. The key isn't hidden in some super complex formula. Nope. It's something you use every single day, probably without even thinking about it. I mean, have you ever just stared at a giant construction crane or a skyscraper that seems to defy gravity and just wondered, how does it all stay up? It's dealing with this whole symphony of pushes and pulls, twists and tensions all at once. So how do engineers manage all that complexity without it all just coming crashing down?
Well, the answer, believe it or not, isn't locked away in some advanced textbook. It's actually in an action that is so simple, so intuitive, you've probably already done it half a dozen times today. We're talking about opening a door.
Now, to really get the secret of the door, we first have to be on the same page about one basic concept. It's an idea that governs absolutely everything, from a floating feather to a freight train. Let's talk about forces. So at its simplest, a force is just a push or a pull. But for an engineer, that's not nearly enough information. It's not just about how hard you're pushing. They also have to know which way you're pushing. And, this is the critical part, where you're applying that push. Those three things, the magnitude, the direction, and the point of application, are the essential ingredients. And this brings us right back to our door. This simple object is actually the perfect little laboratory for understanding how forces really work. So let's break down this seemingly simple action. Think about it. When you open a door, you instinctively grab the handle, right? As far away from the hinges as you can get. Why? Because it's easy. You're using a nice long lever. Now try pushing that same door open right next to the hinges. You know what happens. You have to push so much harder to get it to move. Same door, same you, totally different result, all because of where you push. Okay, now let's add another layer. Let's say you're back at the handle, but instead of pushing forward to open the door, you push sideways, directly toward the hinges. The door doesn't swing open at all. You could be the strongest person in the world, but if your force is aimed right at that pivot point, nothing happens. This shows us the direction of the force is just as important as where you apply it. So this turning effect, this combination of the force, the distance, and the direction that makes the door swing, it has a name. Engineers call it a moment. And honestly, it is one of the most important concepts in all of mechanics. So we've all intuitively felt a moment every single time we've opened a door. Now let's make it official and see exactly why that distance from the hinge is so incredibly powerful. Formally speaking, a moment of a force is just a measure of its tendency to make something rotate. It's basically the rotational version of a simple push or pull. And at its core, you can just think of it as the force you apply multiplied by the distance from that pivot point. That distance, that's your lever arm. It's really just a simple recipe. First, you need an axis of rotation. For our door, that's the hinges. Second, you need a moment arm. That's the distance from the hinge to your hand. Third, you apply a force, your push. You put all those together and you get rotation. The door swings open. And here it is, the punchline. This is why you push on the handle. By making your moment arm as long as possible, you need to use way less force to create the exact same turning effect. It's not about working harder, it's about working smarter by using a longer lever. Okay, so a single person pushing on a door, that's simple enough. But the real world is, well, it's messy. Structures are hardly ever dealing with just one nice clean force. So how do engineers handle all that chaos? Let's go back to our door. Imagine 5 people are all pushing and pulling on it at different spots, all at the same time. One's at the handle, another is pulling near the top, a third is nudging it near the hinge. It's total chaos, right? How could you ever predict what the door is going to do? An engineer can't sit there and analyze a bridge by trying to track a million individual forces from wind and traffic. It's just not possible. They need a tool, a kind of mathematical shortcut, to boil all of that complexity down to one single equivalent outcome. And that tool is called the resultant force. It's a really beautiful, elegant concept. A resultant is a single, you can think of it as an imaginary force that perfectly replaces a whole system of other forces. It produces the exact same final effect on the object. So let's go back to our 5 people at the door. We can add up the total turning effect, the total moment, from all their combined pushes and pulls. The resultant is like figuring out where one person could push and with how much force to create the exact same swing all by themselves. This is the magic trick that lets engineers analyze the incredibly complex forces on something like an airplane wing. So we've unlocked the secret of the door. Now let's scale this whole idea up and see how these two exact same concepts, the moment and the resultant, are used to build the entire world around us. Take a giant construction crane. The huge weight it's lifting creates a massive turning moment that is just trying to tip the whole thing over. The entire design of the crane, especially that huge counterweight on the back, is all about creating an opposing moment to keep it in perfect static balance. Or look at a big electric transmission tower. It's getting pulled on by these heavy cables from all different directions. Engineers just calculate the resultant force of all those cables to figure out the one single combined pull, and then they design the foundation to resist that. And look at this boom lift. Every single pin, every bolt, every hydraulic cylinder in that whole assembly, it's all part of the system. By calculating the moments and resultants throughout the structure, engineers can figure out the exact force that every single component has to be able to support, making sure nothing fails under pressure. And that's really the big aha moment here. From a simple door hinge to the most complex piece of machinery you can imagine, the underlying principles are exactly the same. It all comes down to understanding these turning effects and knowing how to simplify them. So the crucial points to take away are these. A moment is a turning force, and a longer lever arm is always your best friend. A resultant is the tool that takes a chaotic mess of forces and makes it simple. And most importantly, the simple physics you use every day is the very same physics that builds our world. So, the next time you open a door or use a wrench or even ride a bike, just take a second to think about the moments and forces at play. Now that you know the secret, what other everyday objects will you start to see as the tiny, brilliant feats of engineering they truly are?